What was there before the Big Bang? Scientists have been trying to answer the question of what existed before the Big Bang for years, but new discoveries are providing surprising information. Brian Cox and other experts have shown that the answer may be a lot trickier and scarier than we initially thought. According to Cox, the common idea that the universe was hot and dense before the Big Bang might be wrong. Instead, he suggests that the universe was cold, empty, and growing very quickly. This rapid growth, known as inflation, is what shaped the universe into what it is today. However, inflation didn't occur everywhere. It stopped in some areas, which we now refer to as the Big Bang, but continued in others. This idea, called the inflationary multiverse, proposes that our universe is just one of many. According to this view, the universe is like a fractal, with an endless number of Big Bangs occurring in different parts of space and time. Each of these areas develops into its own world, and ours is just a small part of a much larger cosmic landscape. What is inflation, and why did science find it strange? Before the Big Bang, space grew rapidly, a process called inflation. This expansion was driven by a strange kind of energy. During this time, space stretched so quickly that the universe appeared flat and even, smoothing out any irregularities. Eventually, the energy responsible for the rapid expansion was released, heating up space and forming the particles that make up everything around us. The Big Bang, which was once thought to be the beginning of everything, now appears to be just one part of the universe's history. This raises new questions. What existed before inflation? Also, why does the universe continue to expand? The universe is never truly empty. The concept of absolute nothingness doesn't apply in space because, despite the vastness, the universe wouldn't be entirely empty even if we removed all its energy. New types of energy are constantly being created as space expands. Even in the absence of particles, photons, or radiation, quantum fields, foundational elements of reality, continue to exist, ensuring that the universe never reaches a state of complete emptiness. Can there be nothingness before the universe? Is it possible that there was nothing before the universe? According to current understanding, space still holds some energy, even when it appears empty. This zero-point energy is the closest thing to nothingness, but it still represents something, the lowest possible energy that exists everywhere. The universe is constantly evolving. As space grows, it pulls galaxies further apart and cools the universe overall. In the beginning, after the Big Bang, the universe was hot and dense. But as time passed, it became larger, colder, and less dense. As space grows, the light from distant galaxies stretches, which is why we observe redshift, when light waves from galaxies appear longer as they move away from us. This stretching reduces both energy and temperature, which is why the universe is much colder now than it was initially. What would be left if all matter and energy were gone? If it were possible to remove all matter and energy from the universe, what would remain? Empty space, governed by the laws of physics, would still be filled with quantum fields. Dark energy, a mysterious force accelerating the expansion of the universe, would continue driving growth even if there were no particles or radiation present. Thus, even in the absence of matter, the space would still expand, and the universe would continue its evolution. Inflation and the history of the universe. The period of rapid expansion before the Big Bang, known as inflation, played a crucial role in shaping the universe. Before inflation, the universe likely contained a very strong form of energy that caused space to expand at an unimaginable speed. This rapid growth smoothed out any irregularities, creating the even, flat universe we observe today. However, inflation raises several important questions. Where did it begin? If inflation continued indefinitely in some regions of space, generating an infinite number of Big Bangs, how should we view the Big Bang? To answer these questions, we must examine three key concepts: the hot Big Bang, the theory of cosmic inflation, and the idea of an ultimate beginning. The Big Bang and the theory of inflation. Astronomers like Edwin Hubble and Vesto Melvin Slipher observed in the early 20th century that galaxies were moving away from us. This led to the idea that the universe is expanding, which in turn suggested that the universe was once much smaller and denser. This concept gave rise to the Big Bang theory, proposing that all matter and radiation were compressed into a single point with infinite temperature and density. However, the Big Bang theory alone couldn't explain several observed phenomena, such as why the universe is so flat and has a constant temperature. Inflation theory provides an answer, as it may have been inflation that made the universe so flat and smooth. Importantly, this suggests that the Big Bang was not the true beginning of the universe, but rather a transition from the state of inflation to the hot, dense world we know today. Problems with the Big Bang theory, horizon and flatness issues. While the Big Bang theory explains many aspects of the universe, it has some significant issues. One is the horizon problem, which asks why distant parts of the universe that have never interacted with each other have similar temperatures and properties. According to inflation, everything was once closely linked in a small, dense state before rapidly spreading apart, which explains the uniformity we see. Another issue is the flatness problem. The universe appears to be perfectly flat and stable, yet the forces of expansion and gravity should have caused some curvature. Inflation solves this by stretching the universe so much that any initial curvature was smoothed out. Additionally, inflation theory explains why we don't see unusual particles, like magnetic monopoles, which should have been created if the universe had been too hot. What happened before the Big Bang? The question of what happened before the Big Bang is still open. In 1980, physicist Alan Guth proposed the inflation theory, which provides a potential explanation. He suggested that before inflation, the universe's energy wasn't split into matter and radiation as it is now. Instead, the energy was part of space itself, causing the universe to expand at incredible speeds. Inflation solves three key problems in cosmology: the horizon problem, the flatness problem, and the monopole problem. Inflation theory also provides insights into how galaxies and other cosmic structures came to be, as small quantum fluctuations in space grew over time, eventually forming the universe as we know it. Inflation and the multiverse. Although inflation theory has greatly enhanced our understanding, it also leads to a crucial question. If inflation explains what happened before the Big Bang, does that mean the Big Bang wasn't truly the start of everything? The original Big Bang model suggests the universe originated from a singularity, a point of infinite temperature and density. However, inflation complicates this idea. Because inflation expands space at an exponential rate, it would take infinite time for the universe to reach a state of no size, as the Big Bang model suggests. This challenges the notion that the universe began from a singular point. Additionally, since inflation continues indefinitely in some areas, creating an infinite number of Big Bangs, it raises the possibility of a multiverse, a collection of many pocket worlds, each with its own Big Bang. This process erases any trace of what may have existed before inflation, making it almost impossible to determine how the universe began. The mystery of eternal inflation and the multiverse. Eternal inflation presents an intriguing idea, but it doesn't provide a clear answer to where everything came from. Studies suggest that the expanding fabric of spacetime can't go back in time forever. It must have originated from a different state. This implies that inflation doesn't offer a complete answer to the question of the universe's origins. Other models, such as circular or bouncing cosmologies, propose that the universe goes through cycles of expansion and contraction, but they, too, struggle to explain the beginning of everything. What does nothing mean? The question of where the universe came from leads to a broader question. What does nothing really mean? Quantum fields still exist even in the emptiest parts of space. These fields move and interact, even in the absence of particles or energy. In other words, the closest we can get to nothing is still something, a vacuum filled with quantum potential. The vacuum origin hypothesis suggests that the universe may have originated from a quantum fluctuation in this vacuum, a theory that has fascinated physicists for years. While this remains speculative, it offers an interesting perspective on what nothing really means. Quantum fields and virtual particles. The universe is not made of just space. According to quantum field theory, energy fields fill all of space. These fields interact to create everything from atoms to stars. Even in their lowest energy state, called the vacuum state, these fields are still active, producing virtual particles that appear and disappear in an instant. These fields and particles are fundamental to the structure of the universe, but they complicate our understanding of nothingness, dark energy, and the universe's expansion. Dark energy, an unknown force, is responsible for the accelerated expansion of the universe. While inflation explains the rapid expansion in the early universe, dark energy now causes the current expansion. Even in the distant future, when all the stars have burned out and matter is spread thin, dark energy will continue driving the universe's growth. This means that the universe has never been, and will never be, completely empty. Growth, radiation, and quantum fields will persist as long as dark energy remains. Conclusion: embracing the mystery. For decades, scientists have sought to uncover the secrets of the early universe, and inflation theory has revolutionized our understanding. Yet, as we've seen, it also raises new questions. What existed before inflation? What triggered it? And why does the universe seem to reject the idea of nothingness? While we may not have all the answers, the search for them is far from over. As we continue to explore and refine our ideas, we get closer to understanding where everything in the universe came from. As we delve deeper into the mysteries of the universe's origins, the implications of the inflationary model challenge conventional thinking and continue to reshape our understanding of cosmology. One of the key aspects of this model is its ability to explain not only the structure of the universe but also its ongoing evolution. As we explore the expansion of space and the role of quantum fields, we begin to realize how complex and interconnected these processes are. One of the central concepts in modern cosmology is the role of quantum fluctuations. During inflation, tiny fluctuations in energy levels created small differences in the density of matter throughout space. These fluctuations would later grow into the vast cosmic structures we see today, such as galaxies, stars, and clusters of galaxies. These minute changes, though imperceptible in the early universe, laid the foundation for all cosmic structure. The significance of these fluctuations is not just in their ability to form structure, but also in the way they preserve traces of the universe's infancy. The cosmic microwave background, CMB, which provides a snapshot of the universe when it was just 380,000 years old, contains evidence of these early quantum fluctuations. Furthermore, the ongoing expansion of the universe under the influence of dark energy brings forth the possibility of a continually changing cosmic landscape. This ongoing expansion, observed as the universe continues to stretch and galaxies move farther apart, suggests that even in the far distant future, the cosmos will remain active, with new phenomena emerging as time progresses. While the end state of the universe remains uncertain, the existence of dark energy assures that the universe will continue evolving, albeit in a much colder and more diffuse state. The introduction of concepts like the multiverse and eternal inflation adds additional layers of complexity to our cosmological models. These ideas not only challenge our understanding of the universe's origin but also redefine what it means for something to exist. If our universe is part of a vast multiverse, then the concept of beginnings and endings takes on new significance. Each pocket universe within the multiverse could have its own set of physical laws, making the notion of a single, unified beginning even more elusive. In this framework, the start of the universe could be just one chapter in an endless story of cosmic creation, stretching beyond the boundaries of what we can currently perceive or measure. Thus, while we are uncovering more answers about the universe's past, we are also realizing the limitations of our understanding. The quest for knowledge about the origins of the cosmos remains one of humanity's greatest intellectual challenges, pushing the boundaries of science, philosophy, and imagination. As researchers continue to explore the implications of inflationary theory and the possible existence of a multiverse, new questions are constantly emerging, pushing the limits of our understanding. One key area of inquiry is the relationship between quantum mechanics and general relativity. These two pillars of modern physics work well in their respective domains. Quantum mechanics governs the behavior of subatomic particles, while general relativity describes the large-scale structure of the cosmos. However, when trying to explain the very beginning of the universe or the extreme conditions at the heart of black holes, the two theories conflict. Reconciling quantum mechanics with general relativity is one of the most significant challenges in physics today, with potential breakthroughs that could revolutionize our understanding of space, time, and the forces that govern them. One possible path to reconciling these theories is the development of a quantum theory of gravity, which could bridge the gap between the microscopic and macroscopic realms. This theory might explain how the smooth, continuous fabric of spacetime, as described by general relativity, can also exhibit quantum properties, such as superposition and entanglement. If successful, this would not only improve our understanding of the Big Bang but could also have profound implications for other cosmological phenomena, such as black holes and the very structure of the universe itself. A quantum theory of gravity might also offer insight into the nature of the singularity, the point where both gravity and quantum effects are expected to be at their most extreme. Another avenue of exploration is the role of dark matter, which makes up a significant portion of the universe's mass but remains invisible and undetectable by traditional means. Although dark matter has yet to be directly observed, its effects on galactic rotation and the motion of celestial bodies suggest that it plays a crucial role in shaping the large-scale structure of the universe. Some theories propose that dark matter could be connected to inflationary processes, and its properties could offer new insights into the forces that shaped the universe's early moments. As cosmologists delve into these questions, the search for the ultimate origin of the universe becomes ever more intricate. Theoretical models may continue to evolve, incorporating new data and refining our understanding of cosmic events. However, the true nature of the universe's birth and its future evolution may remain elusive, awaiting the development of new scientific tools and breakthroughs that will one day unlock the secrets hidden in the depths of space and time. The pursuit of these answers is not only a scientific endeavor but also a philosophical one, as humanity seeks to understand its place in the vast and mysterious cosmos.